Welcome back, and we're doing another video again, and we're still on springs. This is going to be the third video about springs, and we probably got two more to go, and then we're done, and we'll go back to other things. So in the last video, we were dealing with applying springs to a single bone in an armature. So this way you can control certain little bits and pieces. That turned out pretty good. In this video, we're going to explore chain of bones, and the way you apply these springs on chains of bones is a little bit different, and what you can use chains or bones really is to control hair and clothing and things like that. So this allows us to do a lot more things, and I got some fun demo to show at the very end of a tentacle, of an octopus tentacle being controlled by a chain. So first of all, we're going to start off with some basic stuff. So we have a cube, and on the cube I have a 3-bone chain. No, actually 4-bone chain attached to it. And at the very top, I threw a little cube that's attached to the end of the chain. And I fixed up the armature system, so now this works beautifully, exactly how it's intended to. Unlike last video. The parent-child thing I fixed up. So let's look at some code. So I got some new code in here. I don't remember if this was in the last video. It's been like 2 or 3 weeks. But I added some things in here so this way I can control the animation tests. So I can just press 1 through 6 and go back and forth with different types of animation tests. Everything else is pretty much the same. Just a lot of this setup code. And so last time we created a ECS component, just a jiggly. So this way you can just jiggle one bone and that's it. So then I guess the naive approach, would just basically say, well, let's just grab 4 bones and apply the jiggly component to it and give them basically all the exact same value. And this is what we did. This is what I did. And I press spacebar to start up the animation. You can kind of see bones, just the back and forth animation is just not so good. Circle animation, again, not so good. You can't do that. Every single bone cannot have the exact same values because this is what you're gonna get. It just doesn't work well. It doesn't work the way you intend it to. All right, so again, obviously that's not the right approach. So you don't want to have the exact same settings for every single bone. So what we can do is, well, okay, let's take every single bone and apply different values to it. So we're going to apply a different damping value and a different oscillations per second value. And I added a new function called raw. I don't think this is in the last video. In the last video, we kind of showed you how to calculate the dampening value, the damping ratio. So you can make it so everything's timed correctly, but you don't actually have to calculate. You can just pick a value for damping ratio. As long as it's between 0 and 1, you're pretty golden. Like the value of 1 will give you a critical damp, so there'll be no spring whatsoever. So I create a raw function, so this way I can just put the raw value in there. So this way is a lot easier to then change it. So I don't want to do all that mathematics. Just here's a raw value, like sequentially. So say the first bone is going to be 0.4. It's going to be more springy, and the further down the bone, the less springy it is. So the last bone in the chain is the least springy of them all. And as each spring has less of a spring to it, I also increased the oscillation. So the movement of the spring is faster the further down the chain you go. So it's more dampening and more speed applied to every piece of the chain the further down you go. So if we get that, click refresh. Now we get a very smooth animation. So everything kind of just waves, and there you go. Everything's beautiful. The black dots are the positions, that's the resting position that it wants to be at. And the blue dots are the following points. So if you remember from the previous video, that's how the jiggly bones work. They have a resting position and a following position. And that following position always going after the resting position. And for you can move the resting position. It doesn't have to be actually at rest. It just can be that's the position it should be when there's no springing whatsoever. So as I keep moving the cube, the resting position of every bone kind of gets changed during every animation. So like I said, if we run every single animation test, everything works pretty well. And this one's just like noise movement, and they got noise rotation. And there you go. Beautiful. Ideally, you can say, well, that's it. We're done, right? But here's the thing. When we're running this code, every time you run Jiggly Bone, you actually have to calculate the world space positioning. And you have to make sure everything is in order. So you have to run everything in the right order, and you have to calculate the world position for every single bone. So if I'm at the very last bone, let's say the fourth bone, I have to go through the entire chain to figure out its current world space position. Ideally, you end up processing a lot. So that means, let's say the first bone, I only have to, it only has one parent, which is the cube. The second bone has the parent bone and the cube. So it has to do the calculations for two transforms to figure out its world space position. Then the third bone has two parent bones and the cube. And the fourth bone. So that is, as you see, the further down the chain you go, when we just do a single component on a bone, we actually start doing a lot more processing. So ideally for optimization, if you're going to do chains, treat it as a chain. Treat it as a single object, not as a bunch of multiple objects that you can run it. So the third option is you create a function like, let me get rid of Jiggly because we don't need a Jiggly system anymore. Just create like a function that takes in a chain, and then you can put in certain values in it that can then do all these calculations for you. So you don't have to sit there and manually do anything at all. So like this is actually more work, where if I can just say, here's the starting position, and then down the chain, this is the increment. So let's say I start at 4, now we're increment by 2. So this way it goes 4, 6, 8, 10. Same thing here. I have a value of oscillation. And how do you increment as you go down the bone? At 0.6, and I want to increment 0.2. So it'll increment the exact same value. So this way, I can do all these bones and apply it in a single. So this way, you make first of all, you make the API easier. So if you have a chain, and if you're going to do like a lot of bits of animation, like IK animation, you're going to have a chains in there. You're going to have legs as chains. You're going to have arms as chains. You might have hair as chains. So this way, you treat hair as a single object that can move around. So things like that. So here's my little chain object. So like I said, I pass in my dampening value, like my starting value. Then you increment the oscillation and your oscillation increments. This one's like very, it's like I'm not passing in the armature or anything else. This is kind of like a very simple function that I'm creating. So I'm just grabbing things from global. So ideally, you kind of want to create a class or a type of function that you also have to pass in the armature, or at least pass in an array of bones to treat as a chain. I'm still trying to figure out how to do something with ECS to, create chains. I might do like an IK rig component, and then the IK rig component will then have an array of chains. So this way, I can set up an IK rig component and say, okay, here's the arm chain, here's the leg chain, here's the spine, here's the hair number 1, hair number 2. So this way, it's all in one component, and then has like a collection of chains, because that's really what a body can be if you're doing a lot of IK stuff. So it's kind of just, just collections of chains. So what we got here? So I got extra variables in here. So this way I can kind of use it, so I'm not recreating these variables. Like the vec3 I use is a float32 array, and it's slower to create a float32 array than a regular array. But I like to use float32 arrays because that's what the GPU wants to see. So you pass in so I don't have to do any conversion anyway. The values are already there. And I've had problems where if I use a regular array and I do an addition, like if I do parse int or something, I forget. It converts a numeric value back into a string and then creates these weird bugs. JavaScript isn't typecast, so by keeping float32, even though there's a performance hit, I actually eliminate a lot of bugs I've had in the very beginning when I was doing this. So, hence, create these variables once and then just reuse them over and over again. So this way I don't have to recreate. There's no instant creation hit for creating these variables. Because this, what this function does, it actually just creates all these variables, presets up the initial position, and then it creates a closure. And then I just run the closure on it. And that closure contains everything in one go. It's kind of like a class object, essentially, without having a class whatsoever. I've been doing a lot of Rust, so I'm starting to do more closures instead of creating class objects, because it's easier, and you can do certain cool things that you can't do with class objects at all. So in JavaScript, you can do some fun stuff with closures that you can't even do in Rust. So so why not have some fun? So yeah, we just got a bunch of variables, and like I said in the very beginning, we're gonna get the world position of the first bone. We're gonna calculate its tail because we need to know its end position. Figure out the rest, so we know what its end position is supposed to be. Then we set up a chain, and for every link of the chain, every bone of the chain, we get a follow position, a follow velocity, a follow position, the damping ratio, and this. So every single bone has its own little value, but it's everything kind of stored in an array. So the chain is right up here. And then as the loop goes, I just increment. So I'm not like reusing these variables. Like I'm basically just taking this one value and just incrementing by this. So like I said, I'm just reusing variables without creating a bunch of other things. So this way, the first bone takes the initial, then I do this operation. I just add the increment, and then the next bone in the chain gets those new values applied. And then we have the closure. This is where it actually does all the work. This is basically the update function, the run function. So every time there's a new frame, I say run this function, and it just updates the chain with all its new spring positions. So I guess the first thing we're going to do is calculate the world position of the first bone. Then we're going to save a copy of the world rotation of the parent. So this way we can convert the current bone back to a local space, because right now everything's in world space. We need to convert everything back to local space. Let's see, add bind transform to get bones. So this is finally, now this is where we get the current bone's world space transform. So we get its rotation and we get its position. At this point, then we can we set the tail height. So we create a variable that holds, well, we don't create it, but we set the length, vertical length of our bone, or not a unit length, like a vector length of our bone, and then we use that to transform it based on our world space transform. So this way now, at this point, T-pose, which is our tailbone in local space, gets converted into world space. So that's what this final piece of the puzzle does. We do like a local space to world space conversion. So T-pose is the target position that we want to. It's the resting position. Now we just run our spring equations that we've been running for the last couple of videos. Let's see. We figure out our array. Try to think. Head bone, tail, bone, tail. So we're just gonna do our. I don't know. I forgot. It's been like 2 or 3 weeks. But yeah, this is the same stuff we've been doing for the last 2 videos with springs. Just figuring out the forward direction and the forward direction. No, not this one specifically. Is it? No. Get return to raise, get access and angle. I guess the forward and up direction, and then once you have the forward and up direction, it can just calculate its left angle. I forget. I totally forget what's going on here. I forget what this. I forget what from unit vectors means. There's 2 things that it could be. Well, you know what? Fine. can go to fungi, go to maths, go to quatorians. I'm tired. I was up late last night. Not from access. Oh, okay, it's that thing. Okay, so it takes the two vectors and then figure out the rotation vector between the two by using a cross product, and then at the same time it uses the dot product to then calculate the angle. So this way it actually generates an axis angle based on two unit vectors. Okay, now I'm starting to remember how this works. Okay, so this is the same crap we've been dealing with 2 videos. So I don't want to really bother explaining it. And I have a lot of comments here to make sure you guys follow along. And it helps me remember. So we tack in world space rotation, and then we convert to local space. And then we now this is the part I say that's kind of important. At this point, we already know what the world space parent transform is. At this point, we're going to take our new local space rotation. We're going to take the bind pose position and the bind pose scale, and then add that to our world space position for the parent bone. So that means the next bone in the loop will use our new bone's information as its world space parent information. So this way, when we're going through the chain, we calculate the entire chain once and not do it repeatedly based on the amount of chains there are. So like I said, by the time we hit the 4th chain, I already did like 4 plus 3 plus 2 plus 1 times, add all that together. That's how many times I actually went and added transforms together to determine a transform, determine the world space position. So this way, if I do this, I do this incrementally in one loop. I actually save myself a lot of processing time. So let's see, because I remember in mathematics it's called like 4i, so it's like 4 plus, is it multiply plus 2 plus 1, so that's 3, that's 6, that's 10. So that's 10 times. So I did, basically oh my lord, new keyboard. And it's very clicky. Transform plus transform. I did a transform plus transform at least twice. I mean, not twice, at least 10 times if I was doing the the Jiggly method, like where I do a component for every bone. So I'm doing 10. I did added basically 10, more than that, to be honest, because there's a lot of things like I'm doing invert rotations and doing other things. But just to figure out the world space transforms for all the bones, I had to do 10 operations of transform plus transform. Having this loop, there's only 4 bones. I'm only doing it 4. So technically, just on those two, just on that operation alone, it should be twice as fast, or actually more than twice as fast, because I only do it 4 times as opposed to doing it 10 times. So that's why I said you should treat a chain as a single object, and instead of treating every bone as an individual, because you get more optimization this way. And like I said, it makes the API cleaner, because instead of having to assign every single bone, you can set one bone and then apply all the bones based on the increment value that you put in. So like I said, this is, if I wanted to change the increment, I can just very easily just change one value, and then the entire chain gets applied. So this is great. So refresh, and this is what our bone looks like. This is what our chain looks like. No big deal, right? This is how it was when I was just using the 4 jiggies. But now this is the more efficient version of it. And let's look at what the other stuff. So this is, like I said, now I'm just doing this. Instead of having to figure out all the settings for every single bone, like I said, I just change. I'm just changing like 4 values, and the entire chain will get a new, different type of effect. So I said this is more of a stiff. Ooh, that one's broken. Ooh, that wasn't happening on my other computer. Ooh. Something's broken. Oopsie. I gotta love these technical glitches. I'm trying to think. Oh, you know what? Let me start at 5. A little better. Yeah, I don't know why it's acting up. All right, let's do an increment of 4, 5. Let's slow it down just a micron. Almost there. All right, let's just do this. So I'll make it a tiny bit slower, and I started at a different... It's a little twitchy. I don't know if it's because of my computer, because it's a 4K monitor, but so yeah, let's. Oh, you know what? Let's start at a slightly slower pace. Let's do 3. So this. There we go. See, easy mustard. I hate that blur, but that's because it's a big monitor. The recording doesn't look too bad. I don't know. It's hard to tell from here. But there you go. I got a stiff chain. And like I said, this makes it really easy to kind of fix it. So it's always all about the numbers. And this one's a spring stiff. I don't know why I call it springy stiff. Let's see how this one works out. Okay. Yeah, this one's a little wonky. Yeah, I don't know. It's super stiff, but very springy when it changes. It's very springy. Yeah, but it's going forward. It's going in the opposite direction. So, yeah, I have no clue what's going on. This is now how it was working on my other computer. Oh, all right, whatever. You can play around with it. Like you can, I probably off the numbers a little bit. Maybe it's the refresh rate. Oh, you know what? The refresh rate's different. Yeah, it might be a refresh rate issue. My other computer has a 60. No, I think it has a higher refresh rate than like 60 hertz, I think. And this one, I believe, probably is stuck at 30. This might be stuck at 30 frames per second. Display. Is that the... I think that might be it. That actually might be the big issue. Yep, 30%. I can't even get the 60 frames per second. It's at 30 frames. It's really slow. So that's why things are a little wonky. Because the refresh rate of the monitor itself isn't very good. So the other monitor is a lot better because it's a tablet, Windows tablet. All right, so that's really the big issue. Oh, that's going crazy. So, but there you go. This is with the settings are correctly. This one's like if you actually just use like if I'm not trying to be so like strict, just let things move. It doesn't matter what the refresh rate is. Like this one, this is really ideally what you're gonna want, essentially. Anyway, you want more of a flowy, springy thing. Let's see. This video has been going on for 20 minutes. But yeah, pretty much told you everything. So now the thing I can do is just show you with an actual mesh instead of just looking at bones. This one has several bones, and there you go. This mesh actually didn't have bones built into it, and I added bones to it in Blender and had to do weight painting on it. I did an awful job of weight painting. I wish I think I learned recently that you can there's like a blur for weight painting that would actually even things out a little better. But I only learned that like a week ago. So yeah, I could have done a better job. But here you go. Here's a tentacle. But like I said, this is a nice mesh. This is the exact same code as the other one. But now, like I said, instead of moving the bone, just seeing the preview bones, we can actually see the tentacle. So let's say that's just back and forth. If I switch to 2, which goes in around a circle. You get to see that nice transition from one animation to the other. It's like I said, it's just things following each other. And let's see if I go to number 3. And this is kind of just quick movements, just quick random movements. And it works good. Go to number 4. What's number 4? I don't even know what number 4 is. I guess it just rotates back and forth. Number 5, it's let's see. This is a noise. Yeah, noise movement. So I love how it just moves. It flows. Even though the weight painting on this is horrible, it moves very well. Look at that. I love that. Beautiful. That is so freaking awesome. I don't know why. It's feisty. This in Unity is like, okay, sure. But if you built this shit from scratch, holy crap! It feels so much better. It's like, to me, it's like amazing because I did it. You know, like every single pixel, every single vertice. I calculated it. I calculated its movement. I'm sorry. I need more coffee. I get crazy when I don't drink enough coffee. So there you go. That's beautiful. And I get this is just noise rotation. And there you go. It works. Now you can have tails. You can have hair. You can have tentacles. You can do a lot of things. You know, clothing. You know, I've seen certain like skirts. They have these chains. You just move it. I think they might just have to make it a little bit more stiffer. Just configure things to be more stiff. But yeah, there you go. Let me go back to the fun movement. So there you go. So that is springs. This is the first video, and we're now applying springs to bone chains, which is pretty awesome. I already have the code pretty much almost done for the next video. Let's see if I go to demo fungi.sketchpunk.com/demo. Let's see, we can... Do I have it? Yeah, it's called terrain, I think. So in the next video, we're going to deal with applying springs to vertices, but we're not going to do it I watched some videos and like the Unity stuff, and everything's done on a CPU. It's just, you just have a bunch, just basically the same thing we're doing right now with bones. We're just applying them on the CPU, and then we do a calculation, and then we pass it to the GPU where it gets rendered in the shader. So I wanted to do vertices differently. I want to do springs in the GPU with a shader. So once you push everything to the GPU, like all the data, there is no more JavaScript that actually runs the springs or anything. Everything gets run on a GPU purely. So that's what the next video about, and this is like one of the prototypes I put together to illustrate springs vertices. So I'll give you a nice little preview, and it's very springy in the beginning. So these are all vertices, and they're being processed with springs, but on a GPU. And I'm using transform feedback. I did a video probably like almost 2 years ago about transfer feedback. This allows us to keep data on the GPU and have read and write access to binary buffers. And then you do all the math in the GPU and you save it to a binary buffer, and then you can then take that binary buffer and then render it. And this is what's happening here. So, it looks... and I'm just creating terrain, but I actually I have controls set up. So this way I can move through Perlin noise and see its movement. So it's basically like terrain. And if I just move it to the next one, I'm just shifting over the frequency of Perlin. And if I just hold down the button, then I'm just like traversing through it. And then when I let go, everything kind of springs back into motion. So this is what we're going to really focus on in the next video, is doing this all on the GPU. And we're doing this with vertices, because I was going to do one more video, and there's going to be like vertices and then like soft body physics. And I realized some of the soft body physics prototypes I'm putting together, there's some little bit of math in there, so I'm thinking about maybe just breaking it out into 2 videos where just spring vertices, just applying them to vertices on the GPU, and then basically how to set up a transform feedback and everything else. I'll quickly go through transfer feedback and and just to refresh if you don't use it. Like I rarely use it. I had to refresh myself on how to use it. But yeah, it's really great and allows us to do some really funky things. And I can do all this stuff really well because I'm not actually running this on the CPU. So it's just if you have a good GPU on your computer, this runs really smoothly. So yeah, I think this is fun. Scroll wheel to zoom. Yeah, I can zoom in. That's right. Actually, it might be fun. And on top of that, you'll see the shader, how it works. So because I have like two shaders, there's like the transform feedback shader, which is basically kind of like I set it up as like a poor man's compute shader, and then I take the results and pass it into another shader for rendering, and that rendering actually creates all these colors on the vertices. So this way I can so basically kind of like this biodome thing going on where the flat side is where water is, and then you kind of have these light colors where is like beach sand, and then you got some green, and then you got at the really high you got some snow going on. So yeah, so there you go. So now you're inside and you kind of see that. So I thought this might be a fun preview to you guys to see what the next video is about. I just want to finish up some one more prototype for soft body physics. I'm trying to see if I can have a Snorlax model and punch it and have like little punch spots in it and then have it spring. Thought that might be fun as a final demo for a spring soft body physics. And that's all that stuff would be running on the GPU too. So it goes hand in hand. If you're ever really interested, fungi.sketchmark.com, that demo, I have a bunch of crap in there. I'm starting to build up for people to view. I have water. I don't know if I'm going to do a video about this at some point, but when I did the terrain, I wanted to do water, and I actually created this water thing. Not this specific thing, but I actually worked with the equation Gerster to create kind of water waves for work like several months ago. And I decided to take the math equation that I learned and then built this little demo to kind of allow you to kind of control the water. And again, this is all running on the GPU. So yeah, this is all running on the GPU. So the same thing as the terrains, and the line intercepts are actually done on the CPU. So I kind of actually do calculate a little bit of the water on the CPU only when I want to do a ray intersection, and it's a really crappy ray intersection. But again, if this demo that I put together is something worth making a video about it, just tell me. Then I'll schedule it because the code is done. It's all done. There's nothing left for me to do. It's already based off a tutorial that's all exists online. I learned the equations from it, but I can basically do this with the transform feedback and type of stuff. But I can't really explain the math that well. I did a couple of small changes, but whatever. But yeah, again, like I said, demo has a lot of stuff. If you really care, I don't want to waste too much time on this video talking about garbage. I have a face rig thing. If you're curious, doesn't work very well. It's one of those things I need to kind of put. I need better meshes. So yeah, I was kind of hoping to do kind of like a face rig kind of setup where you can kind of control certain things. I can at least open up her mouth. She got a black eye. See, she's got a black eye. Yeah, there's some problems with this rig, so I need to find a better one that has better bone weights, because this one has some bad bone weights, and so certain things I want to do, like make a smile, doesn't work. But it's a nice prototype, just to get my feet wet a little bit and that kind of stuff. So, and I guess I'll show you one more demo. This is gonna be a future video after I'm done with springs. We're gonna start dealing with overgrowth animation. If you've ever seen Overgrowth's GDC talk, I finally figured out how all of it works, or at least most of it, how they got it working. And this is the walking animation they kind of had. And once I got that walking animation going, I kind of wanted to do animation additives. So this is one animation, but then I can just append extra bits to it, and I can kind of control it. I can add like a little bit of spine control, add a little bit of spine cycle. That's kind of like a timing thing. Then you got the head angle. I can head bang. So I think my kids loved it when I did something like this. And they're like, Vegeta, Vegeta's going crazy. Goku is here. Oh my God. Okay, whatever. All right, enough. So this is stuff for the future that I want to do some work. So I have a lot of prototypes. It's the problem is finding the time to sit down, clean up, figure out what to teach, what not to teach, and then once I have that, then sitting down to record. I've actually had today's video set ready to record for I think almost 1 or 2 weeks. It's just when it comes down to Thursday, I think it's like one of the only times I have time to sit and record is then it's kind of like I'm tired, or I don't really feel like it, or life sucks. So no, life is fairly good. It just life could be better. So I'm gonna stop this life blogging part of the video because I'm wasting too much time. And so yeah, I just wanted to give you guys maybe a heads up of some future things that we will get to see. Yeah, so yeah, that request frame function in JavaScript, it's a little wonky because it tries to catch up now, but everything was set up. So, all right, I hope you enjoyed today's video. I hope you learned a lot about springs. If you're bored and really tired of dealing with springs, tell me. Not much I can do because I'm going to do 2 more videos about it. But I'll never touch upon it again if you guys really don't like springs. I'm still trying to find a good model of a female so I can kind of do some hair prototypes and maybe some clothing. Like I want a girl with some simple hair that I can control, and maybe a skirt, so something easy, the kind of movement. So I'm trying to find something good, fun to play with at the same time, not be like very high poly. I want something low polyish, and be nice if I can have some textures. And that's been weight painted because I suck at weight painting, as this model can prove to you how much I don't do weight painting very well. So yeah, that's it. I'll stop it now. And like I said, I hope you have fun. Thank you for some of the new Patreons that have donated. Thank you very much. I really do appreciate it. And yeah, I guess see you guys in the next video. Hopefully sooner than later. All right, bye-bye.